So Lab-9 is on generative model with two parts, part A on Bayesian linear regression and part B on variational autoencoder. Again, this notebook is based on many public resources, which I appreciate very much. And I have set 3 questions. Here are some suggested readings, right? So part A start with some theoretical background, right? So some review of the linear basis function models, likelihood functions, maximum likelihood, right? So then section A2 talk about some more theoretical background and mathematical formulas for Bayesian linear regression, right? So in the lecture, we didn't talk about the math. We just show the examples to explain. But here, it has the math, right? So you can go through the math, and you can. These are also basically reproducing what is in the textbook, right? So you can look at the PRML book as well. It has all the theories, the derivations, the math, the formulas. And what I found most interesting here is the implementation of Bayesian regression, right? So here, basically, we try to reproduce, right? So this is not my code, right? So it's from that public source, which I acknowledged above. So here you can actually regenerate some of the examples in our lecture, right? So this is, for example, this is ground truth, and that is the posterior, right? So then you can sample from that posterior to generate a line, and you can have the predictive distribution, right? Predictive distribution with mean and variance, right? So that's very nice, and you can manipulate the code to deepen your understanding, right? So you can basically reproduce what is what has been shown in the lecture about the Bayesian linear regression. As a posterior, you have narrowed down to a very narrow region, right? So that's something really good. Right, so the next example shows the distributive, the predictive distribution. Right, so that's also trying to replicate again with non-Gaussian basis functions. Right, so it basically reproduce what is covered in the lecture. And so that's the actual code. You can actually generate the results and play with it, right, to understand the uncertainty and the predictive distribution in more depth, right? So that's very nice notebooks. Again, the credit is not mine, right? So, and then for relational autoencoder, I have consulted several notebooks to have this one, which I think is easy to follow and cover the fundamentals, right? So this is mostly from the tutorial, right? The tutorial on autoencoder, and you can read the original tutorial or just go through my notebook, which I think my notebook is more compact, right? So because I want to make it very compact, so I removed some of the materials, but it should cover the fundamentals over here, right? So, and this is a probabilistic modeling, right? It can give you more of the theoretical background, right? So the apple, how it is derived, right? So how it is derived and how the KL divergence is formulated. And my questions are all on autoencoders, right? On autoencoders. And that's a parameterization trick over here. So I have more details over here. There's also a nice illustration over here. Right, so then we go to the coding, right? So for coding, I also consulted several notebooks, and it's used fully connected layers, right? Use fully connected layers, linear, right? So, and use this is basically the training, the loss, right? The loss optimization process. They zoom in to look at the loss and when it's convergence. And here is the original image and some reconstruction from the learned latent representation, right? So that's a very the reconstruction quality should be very good. Then we move on 2D latent space study, right? So that is, we have Z to be only two-dimensional, right? So that's the example, last few slides in the lecture, right? So again, we look at the optimization process. And here, because we are only have a 2D latent space, right? So that is very low dimension, right? It has only 2 dimensions. So you can see the reconstruction is not as well, right? So not as good as above. There's some mistakes, right? Like this is 3, right? But it's actually 2. This is 4, but this is looking like 9, right? So some are good, but some are not good, right? Especially 4. I think 4 is very troublesome, right? So this is 7, right? So reconstruct as 4. And this is trying to cluster, right? Trying to look at the latent space because Z1 and Z2 are 2D, so you can plot it. And we can see, right? So indeed, 4 is troublesome, right? 4 is, you don't see a cluster of 4 over here. So that's why 4 has most mistakes, right? So has most mistakes. And this is a nice manifold, right? So you can generate yourself, right? So which I show in the lecture, right? It is a very nice manifold that you can generate by running the notebook. Again, here, right, you can see the 4 is really have just it's very difficult to see where is 4. As you can see 7, you can see 1, you can see 3, you can see 2, right? But I think 4 is very difficult to identify. That's why it has problem, right? So you can see most of the digits over here, right? So 0 and 8, 6, right? So 7. So that's it, right? So that is the notebook. Okay, so that basically finished our introduction on generative model, right? So it's very deep project topic, right? So there are many other resources. So here we just give a scratch of the surface to have some very basic introduction. So if you have interest, right, so you can use online notebooks and YouTube videos and lectures to learn more and to dive deeper to deep generative models. Okay, that's all. Bye bye.